Welcome back to Unit 4, Lesson 3. Today we're going to be talking about movement across the plasma membrane. And these are the objectives you should be able to achieve by the end of today's lesson. So first we have to take a look at the permeability of the plasma membrane. And here I have the plasma membrane, just a little review from last day. This is our lipid bilayer, or phospholipid to be more precise. These are the polar heads of the phospholipid. And do we remember what charge the phosphate group has? Hopefully you said negative. Over here we have a negative charge. And we will call this the outside of the cell. Fancy word for outside? That's right. Too easy for you guys now. Extracellular. And the inside? Intracellular. And this middle layer I've drawn red because it is hydrophobic. And here, you just have to, these are, this one here is a protein, and it's a channel protein. This one over here is a carrier protein. There may be one feature here we didn't really talk about last day in our model of the plasma membrane, but we talked about way back when in Unit 2, these 4 fused rings. Okay, I'm just going to talk about it down here. Those 4 fused rings are filling in gaps where we have unsaturated fatty acid tails. That's cholesterol. It helps the membrane pack tighter when there's gaps in it, so more cholesterol. Solid or rigid plasma membrane. Less cholesterol, likely to have a fluid plasma membrane. So permeability refers to the ability of things to just cross the plasma membrane. And at the end of the lecture on the plasma membrane, we mentioned how if you were a negative ion, you were to come close to the phosphate head groups, it could actually be repelled. And if you were a positive ion, you got close to the phosphate groups, you'd actually get stuck there because you'd be attracted. So it'd be very tough to move things from the outside of the cell, inside of the cell, they're positive or negative, if we didn't have the help of channel proteins. That being said, there are some things that can travel across the plasma membrane with very little assistance. Okay. So the things that can simply diffuse straight across in either direction, it's nice and thick, are things like oxygen molecules, CO2, carbon dioxide molecules, small non-polar molecules, such as fatty acids, vitamins, steroids, and surprisingly, H2O. Surprisingly, because they have to cross this hydrophobic region even though they're a polar molecule. And they're able to do this in part because they are very, very small, but also some cells have special channels called via aquapores. But they're much smaller than our general proteins, so it's pretty much like diffusion. And due to complex diffusion principles. So we can explain how water is able to cross that lipid barrier, but it requires some math and some explanations that are beyond us in grade 12. Suffice it to say, it's pretty much because there's so much water surrounding the lipid layer, some of it's able to sneak its way across. Okay. In contrast, we have things that can only go through if they go through the channel protein. So maybe they go through a specific carrier, maybe they go through the channel, and these things can transport in either direction. I'm just showing them going in, but they can go both ways. They may need special proteins to go in versus to go out. But things that have to cross through the channels or through the carriers are ions, charged molecules like Na+, sodium, potassium, K+, calcium, Ca2+, and hydrogen ions, H+, and polar molecules, and things like polysaccharides, all the way back to Unit 2, complex sugars, glucose, so even monosaccharide, amino acid, and nucleic acids. So because some things can pass straight through, other things can only pass through when they have a special invitation, we say that plasma membrane is semi-permeable, partly permeable, so some things can pass through, or more importantly, we say it is selectively permeable, meaning that it regulates what molecules, what particles can cross into and out of the cell. Now, to understand a little bit more, I've used the word diffusion a few times here about some of the principles about how things enter and exit the cell. We've got to take a closer look at these words. So diffusion is simply the movement of particles from areas of light concentration we're going to abbreviate concentration using square brackets. Areas blank concentration. Some of you will know this from chemistry. Some of you may not have heard of this before. So from areas of the first blank is higher concentration to areas of lower concentration. Basically the concept, things roll or move downhill. This process does not require energy. It is a natural law of the universe. And it will continue until the concentrations are, you said equal, you got it right. And the fancy word for when things reach equal status is equilibrium. So that definition of diffusion depended on an understanding of what concentration is. There's lots of different ways to define concentration, but the most common way is concentration equals amount of solute in the solvent. So mathematically, we would calculate concentration by taking whatever a solute was, the amount of that, and dividing it by our amount of solvent. And we represent concentration in a variety of units, such as we can go grams per liter, or in our body, we're usually talking about small amounts, milligrams per liter, or we can talk about moles per liter, the unit for which equals molarity, or we can talk about percent, weight per volume of something, or volume per volume of something. Those are all units. You don't have to know how to calculate all these units, but you just have to be comfortable with if you see these or units or hear me use them, I'm talking about concentration. So now we have to just make sure we know what a solute is. A solute is the thing doing, or I should use a better word than thing. Slightly better word. Not a way better word. Still vague. But the substance being dissolved, whereas the solvent is the substance doing the dissolving. And then there's one more term you should know in relation to concentration, and that is solution. Solution is simply the combination of solute plus solvent. Now all this becomes relevant when we talk about what is osmosis. Osmosis is a specific example of diffusion, very specific. Still, all the principles of diffusion apply, moving from high to low, but it is specifically the movement in an attempt to reach equilibrium. So to understand this movement across the semi-permeable barrier or membrane and why the water is moving, we're going to have to draw a little diagram. So imagine that we have a tank. That tank is a semi-permeable membrane or barrier. As well in that tank are solutions of water. And on one side, we have a total of 12 molecules. A very small tank, very small amount of water. And 8 of those molecules are water, whereas 4 of them are salts. And on the other side, you have 8 molecules of salt, and 4 molecules of water. This is our semi-permeable barrier. And it's semi-permeable in that it allows water, but not salt. So between the two, it's much easier for the water to move than the salt. Maybe we could have put in special pump proteins or something that let it cross, but we're starting with a very simple barrier. And these are water. This is salt. So what's going to happen here is we have our salt is the water, our solute is the salt. So we have 4 solute to 8 solvent molecules. So that's a 1 to 2 concentration. And over here, we have 8 solute, 4 solvent. That is a 2 to 1 concentration. They aren't equal. Now, typically, here on this side, the salt concentration is higher. So you can write that high salt concentration, lower salt concentration. But if you look at that, what does that mean about your amount of water? If you have a lower salt concentration, the rest of the volume is taken up with water, so you have higher water. And if you have a high salt concentration, more of the volume is taken up with the salt, so you have lower water. Now we can fix this one of two ways. Typically, we can move the salt molecules over to even it out, so we can move them from this side that way, except for this is a semi-permeable barrier. It's not letting it cross. So the only other way we can fix this imbalance of concentration is to move the water across. And what will happen is the water will move across until balance is reached in the concentrations. So if 4 waters move across, remember, movement of water is diffusion, but it's specifically across the semi-permeable barrier. It's called osmosis. After osmosis, we get 4 solute to 4 solvent on that side, and 8 solute to 8 solvent this side. That's a 1-to-1 concentration. Now, it was just fluke that I picked something that went to a 1-to-1 concentration. It could be a 2-to-1 concentration, a 4-to-1 concentration. That doesn't matter. What matters is the concentration is the same on either side of the barrier. Meaning equilibrium is reached. Now these guys, they don't just stop moving. They're particles, right? What's the only way a particle absolutely stops moving? Anyone know? You said at absolute zero, which is a hypothetical temperature, absolute 0 Kelvin, you'd be correct. So these guys, the water still bounces around a little bit, and once in a while they cross over into the other side and put the concentration off. But very quickly, another one will cross back to the original side to even it back out. That's what equilibrium means. It might be moving back and forth, but overall, there's not a change in what's happening. So we needed to understand that to understand how cells react in solutions, which is really important in situations where we're delivering something like medicine to the body, because if we put them in at the wrong concentration, our cells will die. So we're going to talk about osmolarity in the cell, and we have 3 conditions: isotonic, hypotonic, and hypertonic. And they are quite easy to confuse, so you're going to have to watch this carefully. Come and see me if you have any questions, because it's critical that you know this well. And that is not a subtle hint that this is an ideal critical thinking type of question. Okay. What does the prefix mean? Iso. Well, we've talked about iso before, right? So, iso, I don't know why it's doing that. Iso, if you think about, we talked about iso in terms of topoisomerase, iso in terms of isosceles triangle. Iso means same. So the term isotonic means that 2 solutions have the same concentration. Sorry, I missed that. Same concentration. A hypotonic. Hypo means, well, let's do hyper first, because you probably know what hyper means. What if someone's hyperactive? They have what in terms of energy? Too much or higher. Hyper means higher or greater. So a hypertonic solution, a solution in higher concentration. Yes, I am filming at school in the classroom, hence why you can hear the bell. So it's a solution with a higher concentration, and of course, if you're going to have something that's higher, you have to be comparing it to a second solution, which would be lower. If hyper means higher, what do you think hypo means? That's good. Hypo equals lower. So it's a solution with a lower concentration compared to whatever the other solution is. So if we're to look at the solute concentration in an isotonic solution, so we have two things that are the same. The solute concentration are equal. And if the amount of solute is equal, well, not the amount, but the concentration of solute is equal, then the relative amount of water between the solutions are equal. In contrast, if you have a hypotonic solution, it means you have less or lower, less solute compared to whatever solution you're comparing it to. So if you have less solute, thinking about what we talked about above, what does that mean in terms of your relative amount of water? That's right, if you have less solute, you must have more water. If we're comparing two concentrations. In the hypertonic solution, you have more solute. So if you have more solute taking up more of the room in the solution, then you must have less water. Now here's why that's important. Because when we're talking about the cell, it's a semi-permeable membrane. And what's going to happen is we talk about the concentrations of the solute using the term isotonic, hypotonic, and hypertonic. But what moves isn't the solute, it's the water. Okay? So if we look at the osmolarity in red blood cells, that's 0.9% salt. So if you had an isotonic solution, you placed your red blood cells into an isotonic solution, what would the concentration of the solution have to be? If you said the same, you'd be correct. 0.9%. Okay? Now, what if you place those same red blood cells into a hypotonic solution? What type of number could we have for the hypotonic solution? If you said any number less than 0.9%, such as, let's go with the good old 0.5%, you'd be correct. And if we were to place it in a hypertonic solution, what type of number could that solution have? You said any number greater than 0.9%, you'd be correct. Such as, let's go with 1.5%. Okay. Now, if you place red blood cells into these solutions, water is probably going to move, but how much and what direction we can predict. Okay, so if we place it in a hypotonic solution that has less solute, it will have blank water. There'll be more or less water. That's right. It will have, the solution will have higher water than the cell. And what will happen? Water will move in. This will cause the cell to swell and maybe even burst. The fancy word for burst is to lyse. So this cell has lice because it's burst. In contrast, if you put the red blood cell into a hypertonic solution, one that has more solute, well, that solution will have more solute than the cell, which means it must have blank water than the cell. That's correct. Less. So if there's less water in the solution than the cell, it means there's more water in the cell compared to the solution. So the water goes out. So this equals shrink. Fancy word for shrinks or shrivels is cremates. And then if they were in the isotonic solution, then equal amount of water during that movement. So let's look at this again. Iso equals no movement if you put the cell in this isotonic solution. You put it in a that's hypotonic solution, it moves in. And if you put it in a hyper, it moves out. The way I remember this, the effect on the cell, if logic is failing me, I can't remember it, I'm getting it confused, mixing up the terms and what's happening, I can always go back to this little trick. Hypo makes me think of a big, fat hippo. It's my hippo. So the cell swells up like a hippo. Hypo equals hippo cell. Whereas hyper, that hyperactive person who's running around everywhere, bouncing off the walls, super tall and skinny. So it's a hyper skinny cell. Okay. So how did it get skinny? The water had to move out. How did it get fat? The water had to move in. By the way, I'd like to say that's a pretty good hippo for me. So, there we go. Maybe we should have a little care. Alright, and iso equals no change. Cell is the same. And if you have any questions at all about this, you definitely need to come see me because we need to understand this concept. It's very critical. Imagine a nurse mixing up this idea and instead of giving an isotonic solution, accidentally giving a hypotonic solution and bursting the cells. That'd be very poor. Okay. Now we're going to talk about other forms of transportation into the cell, not just the movement of water. And there's what's called passive and active transport. And this is a reflection of energy use. If you're passive, you don't use a lot of energy. If you're active, you do. So passive transport cross membrane does not require energy. And the reason it doesn't require energy is because particles are moving with the concentration gradient. Laws of nature dictate they're moving from high concentration to lower concentration until equilibrium is met. And molecules just naturally do that and they don't require energy. This is such as diffusion. But there's a special case of passive transport. It includes facilitated transport. And facilitated transport, sorry, there's no S there. If someone facilitates, what does that mean they're doing? You said facilitate means to help. You are correct. Where channel and carrier proteins move particles their concentration gradient. So even though by the laws of nature things should move along the concentration gradient, so for example if it was higher outside the cell and lower inside the cell, they should automatically move into the cell. There's still those barriers. If you're an ion, you can't move through, so you need the help of a channel or a carrier protein. So facilitated still no energy required, but help is required. Then we have active transport. Which if you look up here, the definition is transport across membrane that does not require energy. Active transport is transport across membrane that requires energy. And what would our form of energy typically be in? Who is the energy currency of the cell? Correct, ATP. So most often it's going to use up ATP. Now this could be because either moving against the concentration gradient, such as in digestion. We don't want to just hit equilibrium. 50% of what we eat gets absorbed by our cells. No, we want to do much better than that. So we have to move against the concentration gradient. And in the nervous system, to create electrical current. And the details of that we'll talk about. So either you're moving against the concentration gradient, going from lower to higher concentration area, or you might be using vesicles to transport materials, whether it's inside or outside of the cell, whether it's with or against the gradient. To use the vesicle is like a little crate carrying things, and you actually have to move that crate back and forth to the plasma membrane, then it's going to require energy. So that's one way of describing transport. It could be passive or active. Passive, no energy required, you're moving with the gradient. Active, energy required because you're either moving against the gradient or you're using vesicles to move things. Another way we can describe transport is just whether it's about going into or out of the cell, endocytosis or exocytosis. So both processes use vesicles, which means it is a form of active transport. Means what? Good, we just did it. Uses so endocytosis is movement. Endo means in. Movement into cell via vesicles. Exocytosis. You figured it out by now. That's right. What does exo mean? Oh, we really have three forms of endocytosis. And two forms of exocytosis. So let's look at the endocytosis first. The first one is called pinocytosis. Pino means tiny or little. This is when the vesicles, and here's the vesicle forming over time, moving into the cell. And as it forms, it captures tiny particles. And we call this cell drinking. Flames in liquids and tiny particles. The next one is called phagocytosis. If you think back in grade 11, we learned about something called a bacteriophage. And you guys were supposed to remember, supposed to be the key word here, what phage meant. And phage means, well, pinocytosis refers to cell drinking. Phagocytosis or phagocytosis is how it's said, refers to cell eating. So these bring in larger particles. This phagosome food vacuole might go on and fuse with the lysosome to be digested. And finally, as the name up here says, for endocytosis we have receptor mediated endocytosis, which is the uptake of particles in response to them binding a specific binder, or response to binding a specific receptor. We're going to learn about an example of receptor-mediated endocytosis in the nervous system. So those are our endocytic processes. And our exocytic we actually learned about when we talked about vesicles in our talk about parts of the eukaryotic cell. And remember we had constitutive secretion, sort of a default pathway that always occurs. Which is designed to deliver contents to the plasma membrane and beyond. Or we have regulated secretion, which only occurs in response to the signal from a cell surface receptor. So something will bind to a receptor and cause this to occur. Really cool thing, example, this is insulin causing glucose transporters to move the plasma membrane. So typically, you have this army of glucose transporters, glucose carrier proteins, that sit in vesicles below the surface of the plasma membrane. And when insulin binds to the receptor on the cell surface, those transporters fuse with the plasma membrane and start transporting glucose into the cell. It's a very cool process. And our very last concept of the cell unit is to answer, so why aren't we just one single giant cell blobbing around this world? Why are we multicellular and why are cells so microscopic? I mean, if you haven't figured out by now, they're incredibly complex. Why do we have to cram all that complexity into a tiny little spot? And the answer is Math. What? This is biology. How dare we bring in math? Well, actually a mathematical principle or a mathematical limitation. It's due in part to the fact that there, it's totally the wrong there, sorry, there are physical limitations to how big the cell can get due to the cell surface to volume ratio. Okay, so let's explain this. Nutrients and waste must enter cell surface. That would be its plasma membrane. And greater volume, so the bigger the cell, the greater its volume, equals more need to move nutrients and waste across the surface. And this is where we run into a problem. Because what do you think is going to make it efficient to do this? If you said greater surface area, you're absolutely correct. So let's do a little calculation. Let's draw our cell. Okay, let's see if I can do this. Insert shapes. I'm going to draw a little cube. Here. Okay. And we'll insert another cube that's a little bit bigger. You can tell I'm not a gamer as I can't really click on the right spots. I'm going to draw a slightly bigger cube and an even bigger cube. Now that we have our 3 cubes, and you can just draw your cubes by hand, that's not a big deal. Let's look at the math. I know some of you are shuddering because you're in biology on the pure grounds that you don't like math. But every once in a while, as a biologist, we're going to need math. Some of us actually need it a fair amount when we're biologists. Let's say this cube dimension. And this one is 1 centimeter by 1 centimeter. Make this one 4 centimeters by 4 centimeters. We'll make this one 8 centimeters by 8 centimeters. First thing we have to do is calculate the surface area. Okay, the surface area of one face will be 1 by 1, and there's 6 faces. So we go 1 centimeter by 1 centimeter by 6 faces. So that is 6 centimeters squared. This one's going to be 4 centimeters by 4 centimeters by 6. So 16 times 6, that's 36. That's 96 centimeters squared. Let me double check that over here. Yep. And this one is going to be 8 centimeters by 8 centimeters by 6 spaces. That's 64 times 6. 384. Let's do that. 64 times 6 is 24. 3 is 36. 384. So that equals 384 centimeters squared. Now let's look at the volume. I'm just going to clean up my scrap work over here. Rough work. So let's look at volume. Okay, and if you remember, calculate volume, length, width, depth. It's going to be 1 centimeter times 1 centimeter times 1 centimeter. That's going to equal 1 centimeter cubed. Here, it's going to equal 4 times 4 times 4. Each of those are centimeters. I just left them out because I was running out of room. 4 times 4 is 16 times 4 is 64 centimeters cubed. Okay, and our last one is going to be 8 centimeters by 8 centimeters by 8 centimeters. 64 times 8. We're going to have to do that over here. 32, 48, 51, 512 centimeters cubed. Now, let's look at what's happening to our surface area to volume ratio. The first one is 6 centimeters squared to 1 centimeter cubed. Our next one is 64 centimeters cubed. Sorry, surface area first. It's 96 centimeters squared to 64 centimeters cubed. And our last one is 512. Again, I put the wrong one first. It's 384 centimeters cubed. Squared, sorry. 512 centimeters cubed. Okay. So if we look at this ratio and put it in lowest terms, this is 6 to 1. Okay, I paused and when I got a calculator. I'm going to admit I'm not doing this in my head. 96 divided by 64. This ratio, oh, I should have been able to do that one in my head. This ratio is 1.5 to 1. And this ratio is 384 divided by 512. This ratio is 0.75 to 1. So what do you notice about the trend of surface area to volume as the cell gets bigger? As the cell increases in size, the surface area to volume ratio actually does what? That's right, it decreases. So your amount of surface area to your amount of volume is getting less and less. This essentially creates a traffic jam. So that into or out of the cell effectively. So the nutrient level will go down, the waste level will go up, and eventually the cell will die. So cell will stop growing or die. Or it can save itself, divide into two smaller cells, which can now transport things more efficiently. And this is why we cannot just be one giant cell blobbing along. Okay? We would simply die. Okay? The other reason is because things are more efficient when they are specialized. So we can have smaller cells that are specifically specialized to do tasks throughout our body. So that is the explanation. If you're having a little bit of trouble visualizing that, I'd like you to just imagine Kelowna. And imagine, and they've done this frequently in Kelowna, the only way to get into Kelowna is across the bridge. And if they suddenly allow for the area of Kelowna to keep the city limits the same, they refuse to expand the roadways, they won't expand the bridge, but they allow all the apartment buildings to go up to 20-story apartment buildings instead of 3 or 4 stories, you would have a huge increase in your volume of people, but you wouldn't have a likewise increase in the surface area. And you can imagine we'd have a massive traffic jam trying to get in and out of Kelowna if we didn't improve the bridge, but we let a whole lot more people live in Kelowna. It's exactly what happens as the cell grows bigger. We can't at the same time keep up with the pathways into the cell, so we get that traffic jam. If you have any questions about this